Today what we're going to do is we're going to take a look at applying the slope, midpoint, and length formulas. If you're having any issues with those, I want you to go and take a look at 7.1 and 7.2. Now, if you think about it, if we're looking at a line and a point, the shortest distance could be the distance between any point on this line here is literally like a line distance calculation. Now, in order to minimize that distance, what we're literally going to do is we're going to actually only use 2 points. One that exists off the line and one that exists on the line. Now, actually, if you think about it, the closest point is on the blue line here. And that blue line has a shared point that it crosses with the line segment AB. Now, by doing so, what that allows us to do is it allows us to take a look at the perpendicular line equation and the line segment of AB. Now, what we're going to do is we're going to use those two in order to find a shared point between them, and then use that shared point that exists on both this perpendicular line and the line AB to help us find the shortest distance between those two lines. Now, when we go and calculate a triangle like this, like say figuring out its slopes, we're just going to go and calculate the basic slopes. And what we normally do is something that's similar to this. MAB is equal to negative 3 over 3. We get this. We do the same for MBC, and we do this. We end up with this. And now what we're trying to do is we're trying to check out if there is a right angle. Now, the only time we have a right angle is when our slopes are negative reciprocals of each other. And now if you look at AB, the slope of AB and the slope of BC, you'll notice that these two aren't negative reciprocals. But when we take a look at CA, you'll notice that it is a negative reciprocal of BC. So you would literally say for this problem that this line is literally perpendicular to BC because of the negative reciprocal, and therefore this triangle that we formed is a right triangle. Now, when we calculate lengths, what I want you to do for this problem, we're going to go and practice our exact calculations. So let's do that. So if I want to calculate the distance of BC, we're literally going to get this. And then we substitute, simplify, and we end up with something like this. So the distance of BC is 10. So that's this portion here of our problem. Sorry, AB, this portion here. Now, for BC, we do the same problem again, and we end up with something that looks like this. Now, you'll notice that we have the square root of 20 as our final answer. Now we're going to go and give us the exact answer. And now, in order to do that, we're going to put the perfect square of the factor of 20 in front. So we end up with the square root of 4 times the square root of 5, because 20 is the same as 4 is 5, and we can always split that square root. So now we're left with this. The square root of 4 is 2, root 5. And we can do the same similarly for CA, for its distance. So we end up with something that looks like this. We get to 80. Now, you know that 80 is actually divisible by 16 and 5. So 16 times 5 gives 80. So we can write that out to be the square root of 16, so the square root of root 5. And we end up with this problem here. Now, if we wanted to check to see if this works, what we would do is we would go and do the Pythagoras theorem to compute this. So I'm going to let you compute these. Figure out, check to see if this squared equals this squared plus this squared. If that works, then you know that this is a right angle triangle. Go ahead and check it on your own.